Hi, my name is Andy Fish, and this is Nicholas Risley. And for our senior project, we made an internet control fan coil unit. So, so throughout the throughout the project, we're gonna describe. So we're gonna describe the project and about why we did it, and like some of the core principles, design process into this, some of the engineering considerations in this project, some of the control system acquisition, setup, the verification, and some of the process errors for future improvement. So what is a fan coil unit? A fan coil unit is a piece of HVAC equipment that is similar to an air handling unit, but it's much smaller than an air handling unit. It has inputs and outputs being controlled to optimize system efficiency and to check the status of various components. So what are some major design considerations? Well, first we wanted to be energy efficient. We want to reduce the noise in the unit, uh, the dehumidification, as well as the longevity of the operation. So how will we address them? Well, instrumentation was put into this project. We use sensors such as barometric sensor, temperature sensor, humidity sensor, uh, and to work the control logic. Um, and so like some pre-established criteria. We use appropriate considerations to fulfill what's required. How we do it? So applicable standards, like we use ASHRAE standard 55, which is the thermal environmental consideration conditions for occupancy. ASHRAE standard BACnet 135216. Uh, and some books we had, like we had the handbook 2017, Springer's Energy Efficient HVAC Design, and as well as ASHRAE Fundamentals of HVAC Control Systems.
For the next part of this presentation, we'll be talking about the instruments, the systems that we use. As you can see here, there's a picture of the system that we have. We have like the SCADA system, system control and data acquisition unit. This is the actual air handler unit or fan coil unit or VAV box, whatever you prefer to call it. And this is the control cabinet. So one of the first inputs that's really more one of the most important ones is the pitot tube. And the pitot tube is something that measures both static and dynamic pressure inside of the fan coil unit. And it measures, the change, and then through Bernoulli's equation, they figure out how fast the linear velocity is. Once you times that by the cross-sectional area, we get the amount of CFM. One of the things that we messed up, I guess, through the design process that we weren't aware of was that we were thinking that we should pull the air instead of push the air, which is usually a good design idea because it's much more energy efficient to pull air than it is to push air. But the pitot tube has to be in front of the fan, not behind the fan, we believe, because through pushing the air, from pulling the air, there wasn't enough like dynamic pressure. Even though we could feel the air, it wasn't going through the pitot tube to give a differential pressure for either the analog or the digital transducer. This goes into the actual equation to get the CFM. Once we acquired the CFM, we could use we used a triac circuit in order to use the fan affinity law to figure out what the new CFM would be. By changing the RPM, you could change the amount of CFM, and that was all part of a feedback loop within the control logic. For air purity, that was another major consideration through the design. We used a HEPA filter. We used two MEMS actually. They're the Bosch chips, both of them. We would measure they're atmospheric Bosch chips. We would measure the pressure before the filter and the pressure after the filter. We realized that the pressure before the filter was just going to be atmospheric, so we just used the pressure after the filter because it reduced in the time for wiring and then programming, and then the fact that the library for the Arduino could only acquire the sensor from one of the MEMS due to the library being so expansive. We figured that as the DP as it increased through clogging of the filter, we would set out a light, either green for it's good or red for it's bad. Um, that actually was part of a separate control system from the ALC unit that we had. The triac circuit with the servo motor connected to the potentiometer of the triac circuit. We realized afterwards that we should have used something called a MOSFET, which is actually a transistor. It's a form of transistor that's used in amplifiers. Um, it would have reduced the need for having to take the electrical energy, turn it into mechanical energy just to move the potentiometer to adjust the fan speed. It would have done it all solid state. But we were unaware of that through the design considerations. We couldn't piece together exactly how to do that through any of the standards we had until after we did it. And then someone kind of walked over and was like, hey, you should have used a MOSFET for that, which, I mean, hindsight, I guess. For the temperature sensors, we used two different types of temperature sensors. We used a thermistor, and we used two of these temperature and humidity sensors for the actual application of this. We pulling temperature sensors from the beginning, the middle, and the end, the fan coil, and we would use that for the psychometrics in order to figure out, if there's a loss of like a temperature, like what exactly the correlation is between what we're doing and the actual output, and then we could trend it into the database and then figure out long-term effects of what the controls are doing. Dehumidification, as you can see in the bottom, there's those DHT sensors I was talking about. Ours were a little bit larger, but that's just because they were linear. Those are Arduino ones made specifically for the Arduino, shown in the PowerPoint. We would use a psychometric chart between the heat exchangers. We had a cooling coil and then a heating coil. And as we would move the air through the cooling coil, it would condensate into the condensation pan. And then we would have to reheat the air back up. And then it would change the relative humidity of the air. And we would use those sensors to figure out whether or not it was actually changing the humidity of the air. Unfortunately, through the actual fabrication of it, we never got the chance to put cooled water and warm water in it. But we did get to the point where we could pick up the signals from the electronics. This is a Euler diagram. This is similar to a psychometric chart. It's just kind of sideways, but this is an industrial standard way of describing how the temperature and the relative humidity are correlated. And effectively, we could drop the humidity through cooling the air down this curve, and then you'd reheat the air back up into a point where it's within the ideal temperature diffusing point, where people are more comfortable with having that air diffuse down their back or over their head through the ceiling tiles. This is a close-up image of some of the actual unit again. We created a door here where we could open up to replace the filter. You can see here's a DHT sensor. It's kind of very difficult to see, but there is actually a pitot tube coming up through here. It's kind of blended in with the heat exchanger. There's a condensation pan here in the bottom. And there's two barometric sensors here where they're wired off to the side. So what did we use for the control system? We were very fortunate to have people at Cornell University loan us some of the LGR and SE module ALC controls. These are very, very expensive controls, about $10,000 worth of controls, including a diagnostic board right here, and another diagnostic board right here, and then the repeater right here, where we would repeat we had serial communicating from the LGR to the SE module, and then also another serial communication going to the zone sensor, which measured temperature and humidity and occupancy of just kind of like a wall type of temperature. It's called a T-stat or thermostat. And yeah, so the logic was more easy to work with than what we thought. The most difficult part was the networking. Once we did all the physical wiring of everything, we had to work up the OSI model and slowly get to the point where we could communicate over the internet, which was pretty difficult. But luckily, a lot of the programs that they used for it are all built in-house to make it as simple as possible. but there were some, I guess that they call it undocumented features of the system, also known as bugs. Through demonstration day, we created the server, but unfortunately, the night before, the database got corrupted, and then when we booted it back up in the morning, it was giving us an SQL error for a Derby database, um, which was just it was due to us not duplicating the database because databases become corrupt from time to time, and were we thought that by restarting the computer we would avoid an error like that, but it's actually what ended up causing the error. So instead of using the actual ALC controls to find the filter status, we decided to instead create a smaller Arduino system, where it's more of a closed circuit system. Instead of communicating back to the SE module, we just communicated from the SE module to the Arduino. Why did we do that? Because it was extremely cheap. We didn't have to worry about BACnet objects and protocols. Um, it was we had the opportunity since we already had the equipment. But some of the weaknesses of it was that there was no BACnet, again, for more of a professional look. There was no servo motor potentiometer coupling was really a weak way of controlling the motor speed. In hindsight, we would have used a MOSFET, but through the design, we decided to use a servo potentiometer. And this was really an atypical application of what we did. They would never allow that in industry because they're not reliable enough. This is actually what the web control looks like. This isn't the actual image of the web control, but we will bring it up later through the actual physical demonstration of it. We were more familiar with the software than we are for the other ones. Creating the HMI and SCADA system was actually really easy to do. It took something like a week to become like a really proficient in the software and to create really good looking and sharp images on it. The weakness of doing this in practicality is it would be expensive, because quality doesn't come cheap, and this is very high quality that we're dealing with here. And the opportunity is we already had it, and then again the threat is that it was complicated as far as networking goes, because although the GUI it was more or less easy to make, the actual the experience of using the software got very complicated with creating the code and then linking the code to the graphics, and linking the feedback, and then doing, I mean, it was, I was lucky to have all the standards and stuff, but even with the standards, there was a lot of stuff that was just not covered and was just an issue the entire time. BACnet. I always talk about BACnet, and the reason is because it's absolutely crucial for developing a system like this. BACnet was developed at Cornell University, so luckily I had the ability to had access to the information of creating a system like this. It's an object-oriented language with services running similar to commands. It gets complicated. You have to create these huge tables of different objects. Each object can, represent like an analog input, analog output, digital input, digital output. But this is something that is absolutely crucial in order to create an actual system that could be installed into a building. The fabrication was pretty complicated. There was a sheet metal fabrication. There was the wood shop fabrication. There was the wiring, the cabinet design. This wouldn't have been possible if we didn't have SolidWorks software to help us along the way. To even Visio. Visio was really helpful for designing the cabinet. Inside the cabinet, getting all the ductwork to line up. It wasn't by happenstance that everything kind of fit in there. We used every square inch thanks to like intelligent design through using software. The NEMA enclosure, that's something that we paid for out of pocket. That was like about $100, but it was it's very it's very professional. I think the way that it works. This is something that you could actually install in an industrial building, and no one would bat an eye at it. So the sheet metal fabrication was probably the most difficult part of this project. we both didn't have any experience with sheet metal fabrication, and we had made friends with some people that did HVAC here at Wellsville, and they told us, well, if you're going to build an actual piece of ductwork, you're going to have to do a Pittsburgh seam. And we went from learning what a Pittsburgh seam is to, actually performing one, building it. Um, just hammering for like a week and cutting yourself on sheet metal, even with gloves on. It was not, it was fun, but it was still kind of like a learning experience. We brazed the pipes for the heat exchangers in order to fit the Belimo valves on them, but more or less it was all learning through the fabrication part of it. But without the theory and principle, we wouldn't have been able to do the fabrication. Here's another picture of the fan coil unit. On here in a second, we'll switch over to another video and then show you the actual thing close up with a camera and explain what each of the components do and each of the considerations that were made throughout the fabrication and design process. All right, so this is the control cabinet I have here. The control cabinet has a PLC or an SE module. It's known for that particular supplier. This is an LGR. And here is a zone sensor, which if you look here is just a T-stat, or thermostat, that does occupancy, temperature, humidity, and different controls, actually. You can control an air handler unit for one of these, surprisingly, actually, just for basic things. This is a digital pressure transducer, differential pressure transducer, actually. Here's emergency on-off for the controls, for safety. Here's an analog pressure, differential pressure sensor. Here is the pneumatics that come here all the way to the pitot tube, which we'll show here in a second. Connector block, which connects down from the PLC, where the bottom then connects into the sensors. And then from here is a electrical line for the gray, and this one here is an Ethernet cable. This entire unit actually is made to be torn apart, and with the bolts and stuff could be easily disassembled and fit into 2006 Nissan Sentra, which surprisingly it does. Over here we have the actual air handler unit. This is the Arduino, which does secondary controls separate from the ALC. We feed the ALC into this control right here, which is an analog 0 to 5 signal. We did satellite batteries here in order to save down on the wiring. Here's some more connector blocks, which connects into the transducers. The Belimo valves, we're very fortunate to have Professor Weegen, who knew a little bit about this, and told us that these were servo motors, which actually completely saved us because we were actually wondering how we could actuate these because they were just known as Belimo valves. Over here we have the damper actuator. By adjusting the Belimo valve, we can adjust the position of these, thus turning this unit into a VAV box, variable air volume, also known as. Breadboards were used for a lot of the wiring. They're normally used for prototyping, which is about exactly what this is. Over here we have an inside look of what's in the unit. We have you can kind of make out the heat exchanger. These are two MEMS. We have here we go. We have two MEMS. We have a temperature and humidity sensor. Here's a pitot tube. We can make it out better now than what you could from the PowerPoint. Two heat exchangers with the condensation plate and stuff in order to keep all the condensation, or the condensation pan, as it's also known in English. Over here we have the actual terminal. The terminal right here, we have pulled up the actual SCADA or the HMI, where you can actually interact with this and then change the different set points. The area, this is typically a building, and then you click on the room of the building, and then it brings you into the actual equipment controlling that room. We just did the entire state because this is a modular thing. Here's part of the actual controls network. This is how the network is built. Everything runs through here, and then that communicates with the server, and the server runs the different configuration of the network, and then you can log on to it through the internet, thus making an internet-controlled fan coil unit.
Okay.
Yep, that's it.
Okay, thank you. If you have any questions, you can email me or Nick, and the email is provided.